Let's look at an example of finding extreme values of a more advanced function without having to sketch the graph. So we just want to use some analysis or algebra, whatever you want to call it, to figure this thing out. So here's the function. It's tangent inverse of 2x minus x. And we want to find the extreme values of this function on the closed interval from 0 to pi. So we know tangent inverse is continuous everywhere on its domain, which is for all real numbers. Certainly x is continuous everywhere. And so f is a continuous function. We're on a closed interval, so we should expect to get extreme points, right? We should expect to be able to find an absolute maximum and an absolute minimum. How do we do that? Well, remember, we want to rule out, right? So there's infinitely many points in 0 to pi, but we want to rule out all but just a couple, right? So we want to find the critical values where there might be a local max or a local min. That could also be a place where there's an absolute max or an absolute min. And then we want to check the endpoints. So step number one, find the critical values, right? So how do you do that? Well, take the derivative. So the derivative of tangent inverse of 2x, right, it's 1 over 1 plus the thing in the parentheses squared, and then tack on the derivative of the thing in the parentheses. So here we get 1 over 1 plus 2x quantity squared, and then multiply by 2, and then the derivative of x is just 1, so we subtract 1. So if you like, you can write this fraction as 2 over 1 plus 4x squared, right, if I square everything in the parentheses, and then subtract 1. So in the next line, I'm just going to subtract these two fractions, right, using the bow tie. If you like, you can write this thing over a 1, and now it's 2 times 1 minus 1 times the quantity 1 plus 4x squared, so make sure you're careful with parentheses here, right? And now this thing simplifies as 1 minus 4x squared over 1 plus 4x squared. And whenever you can, you might as well go ahead and factor the numerator and the denominator. So we can factor the numerator as 1 plus 2x times 1 minus 2x, and the denominator is not going to factor, at least over the real numbers. So what are the critical values? It's where the derivative does not exist or where the derivative is 0. So this thing is a rational function and the bottom is never 0. That means the derivative exists everywhere. So f prime of x exists for every x in the real numbers. What about where the derivative is 0? Well, the derivative is 0 if and only if the numerator is 0. And where does that happen, right? This thing is 0 when x is negative 1/2, and this thing is 0 when x is equal to positive 1/2. So here are the critical values for the function f on this interval. So we need to plug these two things in to the original function, and then we need to plug the endpoints into the original function, see which number is the highest and which number is the lowest. That'll be our absolute max and absolute min. Okay, now that we've found the critical points, we need to plug those critical points back into the original function, and we need to plug the endpoints of our closed interval back into the function. So when I plug in negative 1/2 into the function, I get tangent inverse negative 1, and then minus negative 1/2 is plus 1/2. So, you know, tangent inverse of negative 1 is negative pi over 4. And so I get negative pi over 4 plus 1/2. Well, pi is approximately 3, so this thing is roughly negative 3/4 plus 1/2, and so I get negative 1/4. So I think all that will matter here is that this is a negative number, right? When I plug in 0, I'm going to get 0. So I know that 0 can't be an absolute minimum because there's some y value that's smaller than 0 up here, right? There's some negative number up here on the board. F of 1/2. Well, when I plug in 1/2 everywhere I see an x, I get tangent inverse of 1 minus 1/2. Tangent inverse of 1 is pi over 4. And so minus 1/2, excuse me. So here I'm going to get roughly 3/4 minus 1/2, so that's positive 1/4 roughly. So here I get a positive number. That means 0 is neither an absolute minimum because of this thing, nor is it an absolute maximum because of this thing. So we can rule this out, right? This is not going to give us an absolute max or an absolute min. Finally, I'm going to plug in the endpoint pi into the original function. And so when I do, I get tangent inverse 2 pi minus pi. Well, tangent inverse of 2 pi is nothing special that we know of, right? It's not like tangent of 2 pi. That we would know how to compute. This thing we don't know how to compute, so we need to do a little approximation. Here's what we know. We know that tangent inverse of anything is always between negative pi over 2 and pi over 2, right? Tangent inverse is bounded, right, because tangent has vertical asymptotes, negative pi over 2 to pi over 2, so tangent inverse is always between negative pi over 2 and pi over 2, right? So here's an inequality that'll be helpful, right? Tangent inverse of anything is between negative pi over 2 and pi over 2. So now I'm just going to subtract pi from everywhere. So that says negative pi over 2 minus pi is less than or equal to tangent inverse of 2 pi minus pi is less than or equal to pi over 2 minus pi. So now you work all this out. The thing on the left is negative 3 pi over 2. The thing in the middle is exactly f of pi. And the thing on the right is negative pi over 2. So we know that f of pi then must be a negative number, right? It's between negative 3 pi over 2 and negative pi over 2. So f of pi must be negative. And negative pi over 2 is roughly 3/2. So roughly negative 1/2. So that means f of pi is smaller than negative 1/4, right? So here we've got our absolute maximum, right? So I'll write it here. So the absolute max is at x equals 1/2, and the absolute maximum value is y equals pi over 4 minus 1/2. Right, so there's a good final answer for absolute maximum. And then for the absolute minimum, right, the absolute minimum, that's going to be at x equals pi. And the absolute minimum value is y equals tangent inverse of 2 pi minus pi. Right, so here would be, right, this thing here would be a good final answer to this problem, right? So we found an absolute max and an absolute min to the function tangent inverse 2x minus x on 0 to pi. Okay.